Hi everyone, I'm Anish and welcome back to PrepFusion. So today we will be studying the lecture 8 of polar plots. So this will be the last lecture of polar plots. In this we'll learn one more new concept, right? Which is gain phase plot, and we'll do a few questions on gain phase plot, like one question only, and also a few gate PYQs and other questions, right? And we'll wrap up this topic of polar plot. So from the next lecture we'll start with Nyquist plot. Obviously if we are able to solve other questions in this lecture, else I have to take another lecture, okay? But that is the plan. And like in the previous lecture also we learned few concepts, right? How to draw the polar plots for NMPA systems, how to draw the polar plot for open loop zeros when open loop zeros are present, right? So all those things we learned. So now let's start with gain phase plot. So what is basically a gain phase plot? So gain phase plot is basically a plot between the gain of my OLTF and the phase, right? Okay, so with the variation of frequency, so as my frequency is varying, how, like, where is my phase and where is my gain, right? Let's say I am taking a transfer function whose gain phase plot is like this. What does this mean? I would explain to you what does this mean. So what I am observing is, like, this x axis is the phase axis, right? Phase angle axis, and the y axis is the gain axis. So, like, what are the parameters that I can find? So from the polar plot, what I could have found out, the gain margin, phase margin, and the omega PC, omega GC, right? Omega phase crossover frequency and gain crossover frequency. So here also I can do the same, right? With this gain phase plot. So this is also another way to find the phase crossover frequency, gain crossover frequency, and gain margin and phase margin, right? So because phase, gain, all of them are present. Okay, yeah, this is also used to find the relative stability parameters. So for my omega PC, what is the condition? How to find my omega phase crossover frequency? The phase crossover frequency is the frequency at which my phase of my OLTF, right? It is minus 180 degrees. So I can observe that it is minus 180 here. So obviously I will draw one line parallel to the this magnitude axis, right? Then I will check where does this cut in the gain phase plot. So if I draw a line parallel to the this gain axis, basically, okay, and just simply, what do? I just simply do one thing. Just and let me just draw, like, this is the point where it cuts the uh, this response, right? This is some response, some OLTF, some response, right? Okay, and so what is this point known? This point is the point of, like, the frequency at this point is phase crossover frequency, right? The frequency at this point is phase crossover frequency. Now how to find the gain crossover frequency? So for gain crossover frequency, right, I'm like, this is, sorry, I didn't mention it earlier. So in, if I'm going from denominator, like, bottom to up, right? So this is minus infinity to infinity. Now you might ask, sir, why is this minus infinity? Generally we see 0, right? You say 0 to infinity, that is not an issue. From here also we see 0 to infinity, that is not an issue. But here, right, this can be any negative value, right? So like, this is any negative value. So this is also minus infinity phase, right? Phase. And this is like going towards positive, so plus infinity. Okay, but the area which I'm interested in is only in between these, because my OLTF, right, the phase of my OLTF lies between this region only, minus 90 to 270, minus 270. So I will only draw until this part. Okay, and what about my magnitude? So the magnitude, right, it is varying from infinity to minus infinity. So I had to draw the whole part. But you might ask, how is it minus infinity? Gain, how can gain be minus infinity? Just remember, it is in dBs, right? It is in dBs, not in absolute format, right? Not in normal absolute format. So it is in dBs. So if it is dBs, what is log of 0? Log of 0 is minus infinity, right? So yeah, just be careful about that. That's why this axis is from minus infinity to infinity. Okay, I will not explain this further. So somewhere in between 0 dBs will come. And what happens at 0 dB? 0 dB is the gain at which, like, the absolute value of gain is 1. So the gain of my OLTF is 1 at that frequency, right? So if I do the same, right, draw a line parallel to this x-axis. So wherever it will cut, right, like, let's assume, okay, this is just an assumption that my 0 dB axis is here, like, sorry, my 0 dB point is here, right? This is my 0 dB point. Okay, so this is my 0 dB point. Now if I draw a line, right, straight line parallel to the x-axis. Now so, like, it is cutting my OLTF, like, characteristics of my OLT, right? At this point. So at this point, what is my frequency? So the gain at this point is like 1, right? Whatever the phase may be, I don't care about the phase, but the gain I can see it is 1. So the gain is 1. Then my omega g, like this is the frequency, like this is my gain crossover frequency basically. Now let's come to the relative stability parameters, right? About the phase margin and the gain margin. So about the phase margin and the gain margin, so let's say like how to find the phase margin, right? So phase margin is the amount of phase lag that I need to provide to make reach it to minus 20 degrees. So currently my phase is somewhere around here. Okay, let's say this is minus 90 only, I don't care whatever this is. So this is this one only, but I have to take it to this side. So if I'm going towards the left, I have to add a phase lag. That is okay, right? So my phase margin is positive. I have to add a phase lag. Remember the definition of phase margin, right? You have to, how much amount of phase lag you need to add to take it to minus 180 degrees, right? So that like your gain is also 1 and your phase is also 1 minus 180 degrees. It cuts the negative real axis. Okay, it cuts the critical point. So this is the amount of phase margin that I need to provide, right? And this is a positive phase margin. Positive phase margin, right? So let me write here, say positive phase margin, right? So this is positive phase margin. So I will just write phase margin as PM because this is taking too much space. Okay, so phase margin is positive, that is good. So one parameter is positive, right? So that is good. Now let's understand about the gain margin. So gain margin is when like my phase is minus 20 degree and the amount of gain that I need to provide to take it to 0 degrees, or you can say to amount of multiply that amount of gain that I need to multiply to make it 1, right? Absolute value 1. So this is the amount of gain in terms of dB that I need to, extra margin that I need to add to make it 0 dBs, right? Okay, to touch it to the critical point. So from where I'm going, so I'm going from negative side to positive side. So I'm adding something, right? I'm adding something. So I'm adding positive gain, right? I'm adding positive margin. So my GM is also positive this time. So my GM is also positive, right? So GM is also positive. Okay, so in this case, right, what I can say, what I can comment about the system. So like you just by default, if nothing is mentioned, right, if nothing is mentioned, and like you have to only comment about the stability of the system using the relative stability parameters, you will comment the default case where my OLT is stable, right? And if your phase margin and gain margin comes to be positive, you will say system is stable. You don't take care of those points that I wrote it down, right? That I wrote down, that we can't always comment that when my phase margin and gain margin, let's say, even if it's like if sometimes if my gain margin is negative, still my system can be stable. Okay, obviously, yeah, that is the case, but that are rare cases, right? That are rare cases that may occur. But if nothing is mentioned, nothing is told, right, you will assume OLT is stable. And like if only you have to find out stability through phase margin and gain margin, okay, then you will say yes, this is stable. Okay, just remember this, if you have other ways to find the stability, right, you use the other ways. Like with an IQ plot also we can find the stability, that we do, or with the root locus also you can find the stability, or with the Routh-Hurwitz criterion you can find the stability. So I always recommend Routh-Hurwitz criterion because that will give you absolute stability. This is relative stability. Okay, just a thing to note here is that, so this is stable system, this system is stable. Okay, this system is stable. Now let's talk about this second system. Okay, so what is the system? Obviously from here you can't tell, so this is just like to make you understand, right, to teach you. I have one question there, you will solve. So again, right, following the same procedure, right, I will copy this one. I have to draw a line parallel to this 180-degree point, right? So if I I just take this point here, I just put this point. So the location where it is cutting my gain phase plot, right? So this point is basically my what do you say? This point is my phase crossover frequency. So at this point, my phase is minus 180 degrees. So this is my phase crossover frequency. So again, right, I will copy this one, right? And like again, right, I will just assume this time, right, I will put my 0 dB a bit higher. Why? I will make you understand. Okay, so like we'll understand why I'm doing this. Just to like do one thing. So this time, let's say my 0 dB is a bit higher. Okay, here, right, also one more, what do you notice, that my gain crossover frequency comes before my phase crossover frequency. So that is a very important point to notice here, right? So my gain crossover frequency, just wait a second to do this one. Okay, this is that. Yeah, that is fine. This is fine. Yeah. So like what I was telling was that my gain, like omega g for stable, right, for stability also I mentioned another parameter, that my omega p should be less than omega g. So gain crossover frequency should be more than my phase crossover frequency. Okay, so that is also another case, right? Okay, so like yeah, it should reach like one magnitude earlier than my phase crossover frequency, right? So that's why then my gain margin will be positive, right? So if it reaches one magnitude earlier than cutting my negative real axis, obviously the gain will keep on reducing and it will touch here, right? And then my gain margin will be positive, obviously. So if it is a monotonically decreasing function, if the magnitude is a monotonically decreasing function, okay? So yeah, that is also another important thing to note here, right? Sorry, I wrote this one wrong, sorry. This is omega p is greater than omega g. Okay, omega p is greater than omega g, right? So as like omega is increasing, right, omega from here, right, omega equals to 0, and here it is omega equals to infinity. Okay, it is varying like this, just mentioned by the direction itself, right? Just mentioned by the direction itself. Okay, so just these are just a few examples that I want to take to like teach you how to plot a gain phase plot. So now let's plot this phase plot basically. So what do you understand from this one? Okay, I took one wrong case here. Let me just delete this one. Sorry for the interruption. So this was not in the plans. So let's say my 0 dB is somewhere around here. Okay, now can we comment about the stability? I want to ask you, let's say this is my 0 dB, right? This is my 0 dB and this is my minus 180 degrees. Okay, so and this is intersecting at this point. So can you comment about the stability? So what about the stability? So what is my omega p this time? Omega p is here, right, at this point, because this is the minus 180 degree point. And what is my omega g? Gain is also 1 at this point. So omega p equals to omega g itself, right? Omega p equals to omega g itself. What does this mean? This means my system is marginally stable, right? My system is marginally stable. Whenever phase crossover frequency and gain crossover frequency are same, right, my system becomes marginally stable. Also, what I want a phase margin, I need to add none, right? I'm already like when my gain is 1, right, my phase is also minus 180 degree. I don't need to add any phase lag or subtract any phase lag, right? So here from if phase margin also I can say my phase margin equals to 0, right? I don't need to add any phase or subtract any phase lag. Also my gain margin, right, when my phase is minus 70 degree, my gain is already 1 in absolute terms. So if it is 1, right, so I don't need to multiply any gain, or in dB terms, right, I don't need to add any margin to it, add any gain margin to it. So my GM, right, GM is 0 dBs. So from here what I can comment? I can comment that my system, like here, right, from this gain phase plot, I can comment that my system is margin is stable. Margin is stable, right? So this is what I can comment. So let's go to the third example. So what about the third example? So third example, I will again take the axes, right? Take these two axes basically. Okay, but I will move this around, right? Move this around to like obviously cover all the three cases. So obviously stable has been covered, unstable has been sorry, margin stable has been covered. So obviously now we'll cover the unstable case. So what happens in unstable? Unstable case, right? My phase crossover frequency occurs earlier than my gain crossover frequency. Here, right? My gain crossover frequency occurred earlier than my phase crossover frequency. Okay, so if my gain crossover frequency obviously occurred earlier, so obviously my magnitude will keep on reducing, and then it will become something less than 1 when it cuts the negative real axis. So here, right, it will not be less than 1, it will be more than 1 when it cuts the real axis. So let's say my minus 180 point is here, okay, and this is my 0 dB point, right? Zero dB point. Okay, this is my 0 dB point. So this is my 0 dB point. Can you comment about the omega g and omega p, right? So this is my minus 180 degree point. So here I have phase crossover frequency, and here it is cutting. So this is gain crossover frequency, right? Okay, this is gain crossover frequency basically. So now how much amount of phase lag do I need to add, right? So like at this point, right, my gain is 1. How much amount of phase lag I need to add? I need to go in this direction, right, to get to minus 180 degree. So I need to go in this direction. So if I need to go in this direction, right, so I have to add some, not phase lag, I have to add phase lead. So if you would have studied network theory by now, I hope you understand what does lag lead mean. Or you can say I have to add some positive angle. So add some positive angle, not subtract. I have to add some positive angle, right? So yeah, obviously not phase lag. I have to add phase lead, right? So if I have to add phase lead, so obviously this is negative, right? Negative phase margin is negative. So I can say negative phase margin. Okay. And what about my gain margin? So like at omega p, my gain is here, right? I'm something above my 0 dB axis. So I have to subtract some dBs, okay, subtract some dBs because it is already over my 0 dB. It is already past the 1 magnitude point. So to subtract some dBs to get it to 0 dB, right? So obviously my gain margin is also negative this time. So my gain margin, okay, gain margin is also negative this time. So my gain margin is negative. What can I say? I can say that my system is obviously unstable. Gain margin and phase margin both are negative. So what I can comment here is that system is unstable. Unstable system, right? So system is unstable. So my system is unstable. From what this also I can understand that my omega g is less than omega p. So phase crossover frequency occurs earlier than gain crossover frequency. So before even reaching magnitude 1, it cuts my negative real axis, right? So that is an issue. That is an issue. Okay, that's why from here also you can understand. So this tells that, right, before cutting my negative real axis, my magnitude, before my magnitude reaching 1, right, it is cutting my negative real axis. So yeah, this is about the omega g and omega p. Okay. So now let's do a question. Okay, try to take the screenshot or try to pause the video and try to solve this question. So what is this question? The gain phase plot of a linear control system is shown in the figure below, right? Comment about the stability of the system. So you have to comment about the stability, right? So if you want to comment about the stability, what can you see? What can you say about the phase margin and the gain margin? Okay, or what can you say about the omega p and the omega g? So you assume that OLTV is stable, all those things, right? Whenever they are just telling you to find the stability through gain margin and phase margin only, you just assume that if my phase margin and gain margin is positive, then only my system will be stable. If my gain margin and my phase margin equals to 0, then system is margin is stable. And if my gain margin and phase margin are both less than 0, then my system is unstable. Consider these three cases. Okay, simple cases. Okay, so now what I can see is this is the 0 dB axis. So like I didn't mention here, this is the 0 dB, right? This is a 0 dB. So this is the 0 dB. So at this point, this is cutting the gain phase plot. So I will copy this one. Okay. So this is the 0 dB axis. So this is cutting the gain phase plot, right? So basically this point is the omega g. Okay, my gain is 1, and like where is minus 180? Minus 180 is here. Okay, very near, right? So this is very near. So okay, this will be an issue. So what I will do, I just move this a bit here because else, okay, sorry, I will not be able to annotate through this, right? So this will be a bit difficult for me. Oh no, why is this not moving? Yeah, now it's moving, right? So like I will again draw a line parallel to this, right? And this point, right, will be my omega p. Okay, So this point is my omega p and this point is my omega g. So I'll reduce the size of this one. Okay, so let's comment about the phase margin, gain margin, or from here itself you can see, right, my omega g comes earlier than my phase crossover frequency, so it is cutting my negative real axis earlier than it is reaching the later after reaching the gain equals to 1. So obviously system will be stable. From this directly I can directly comment, right? Still let's compute the phase margin and gain margin. Okay, so like what about the phase margin? So my gain is 1 here, right? So I need to provide a phase lag, right? I need to go in this direction to make my phase minus 1t. So I have to provide a phase lag, not an issue. Phase lag is okay, right? Like positive phase lag is okay. So I have to provide a phase lag. So what is my phase margin? Let me bring this to here only, and this will be my phase margin, right? This is my phase margin. Which is positive itself. Which is positive, right? So my phase margin is positive itself. So if my phase margin is positive, now what about my gain margin? What about my gain margin? So gain margin, right? Gain margin I can comment that when my phase like is minus 1t, how much gain margin I have to provide to take it to 0 dBs. So here, right, I'm like my gain is something less than obviously 0 dB, so I have to add some gain, right? Add some margin to it. So let me take this to this side. What I can do? So my gain margin, right? This is also positive gain margin, so I will just reduce the size of this one, take it here. I have to reduce the size further. GM, right? So this is positive. So what I will do is just copy this one. Okay, so my gain margin and phase margin are both positive, right? Both are positive. So like with omega g and omega p also I can say that like the what is the first thing? First thing is my omega g is greater than my omega p. So gain crossover frequency occurs earlier than my phase crossover frequency. So from this also I can say. And what is my second thing? Second thing is my PM phase margin is positive, not that prime minister, right? So prime minister is positive or not, that you guys will decide. So this is positive, so obviously from this I can say system is stable. Okay, so this is how you solve the question like this. So now let's come back to our normal question. So this is a question about the time delay, right? So find the value of delay time t. So delay time is the t if phase crossover frequency for the OLTF is 4 radians per second. Okay, and the OLTF is given. Okay, so what does delay time mean? So as I explained, right, this exponential term is the delay time basically. So like I hope like you have been revising Laplace, right? So if I have something like this, right, x of t minus td, then the Laplace transform of this one, right, will be e raised to power minus like s td into x of s, obviously into x of s, right? So now let's come back to the quotient basically. So my g of s into h of s is this, right? And what is this telling us? So it has told us about the information that my phase crossover frequency is given. So whatever is given, right, you try to find that, then you will get some relation with t with known value, and then from there you will get the value of t, right? So yeah, that's how you proceed in this question. So whatever they have told you, you just try to find that phase of crossover frequency. So how to find the phase crossover frequency? Phase crossover frequency is the frequency at which my phase of my OLTF is minus 180 degrees, or it is cutting my negative real axis. So I will just find the phase of this OLTF, right? So what is the phase of this? Let's first like replace this with g omega. Okay, this is t itself, right? This is minus j omega t. This is by j omega, right? This is by j omega. Okay, so yeah, now like how to calculate the phase, right? Simply, I will not explain it very much. So we have done this multiple times. Phase of this OLT, right? It is simply like 5 won't come here, so it will come out to be like due to this one, right? Minus omega t will come, right? And due to this like the pole at s equals 0 or omega equals 0, obviously what you will get, you will get a, this is a type 1 system, you will get a minus 90-degree angle contribution, right? So this is my angle. Okay, now the problem here is that my omega, right, omega is given in radians per second. Okay, so this t is in seconds, that is fine, but this is given in radians per second. So this is given in radians per second, then I have to convert all this, right, this degrees into radians. Okay, so just be careful while solving the exponential values, right? Just be careful. Okay, you convert everything to radians per second. When we are doing all those things, right, previously what we were doing, we were converting everything to degrees because everything was in terms of tan inverse, right? Tan inverse, that was not an issue, right? So but here it's a issue because I have exponential term like that, and omega t I have, right? And omega is in radians per second, so second will get cancelled but radian will be still remain. So dimension, I hope you understand it, radian will be still remain, so I have to convert this degrees into radians. So this will be minus 180 degrees, right, equals to minus omega t minus 90, but this is wrong, convert to radians. Okay, convert to radians. Now how to convert to radians? So I hope you remember, right? So 180 degrees, like if you ever forget it, 180 degrees means pi radians. Okay, pi radians, 180 degrees means pi radians. Now how to convert? Just use the unitary method. So 1 degree will be how much? Pi by 180, 180, pi by 180, and theta degrees will be simply multiply, right, pi by 180 into theta. Okay, so this is what my theta is. So not theta degree, I want to specify, this is just theta. So yeah, now you just simply wherever you see, right, you just multiply pi by 180, okay, with everything, right, if all of the angles, and you will convert into radians. So let me name this as degrees this is in radians, right, this is in radians. So basically what you do like this, minus 180 into pi by 180, obviously we know this is minus pi, but still to make you understand, right, I'm doing this slowly. This is minus omega t and this is minus 90 into pi by 180. We know this is pi by 2 from childhood, right? Since childhood we all know this. So now like this omega t will be come over here, right, and this is omega p. Actually, sorry, I should write this as omega p because this is the phase crossover frequency basically. So at this phase crossover frequency my angle is obviously minus 180 degrees, right? So like this one goes over here, pi goes over here, I have pi by 2 over here, right? So this is simply pi by 2. And what is my phase crossover frequency? They have mentioned it, right? Phase crossover frequency they have given. This is 4 radians per second. Okay, this is 4 radians per second. So replace t equals to 4 pi by 2. So t equals to pi by 8. Okay, t equals to pi by 8 seconds. Okay, so my t is equals to pi by 8 seconds, right? So my t is pi by 8 seconds, so this is my answer basically, solution basically. So like sometimes you will not be able to solve these types of questions, right? With exponential it is very difficult to solve these types of questions, as I just told you, right? We'll see a few examples, but sometimes you will be able to, if you are like only if you are able to, they will give it an exam, or if you are not able to, right, in exam, if you are not able to solve this equation, so it becomes difficult to sometimes solve this equation, right? So now as everything is in angles, that is fine, only you have to find this one. Okay, but let's say they have given you the time delay, right? They've given you the time delay and you have to find the phase crossover frequency. to find the phase crossover frequency. That also you can find from here, but let's say you had a pole at s equals to 1, then it would be difficult. Then tan inverse term will also come, then it will be difficult to find the phase crossover frequency. So yeah, in that case, you will not be able to find the phase crossover frequency, which is hand calculation. Just keep that in mind. But if they give you the phase crossover frequency, you will be able to find the t. That is okay. In that equation also you will be able to find the t. Okay, but if they give you the value of t and you have to find the phase crossover frequency, that is difficult. That is difficult if there is like a pole at s equals to 1, if there is a pole other than s equals to 0. Okay, so yeah, I will understand, right? So we will take one example, and from that example we will understand. So the example has come up, right? So what do you have to do? You have to compare the gain margin and phase margin between g of s h of s and exponential times g of s h of s. What does this mean? Basically, you take any OLT, right? Any OLT you take, right? So what is the easiest OLT you can take? You take type 0 OLT, right? Sorry, type 1 OLT. So that like only one pole at s equals 0, and you have this. You take this example itself, okay? This example itself, right? So if you have 5 over s, and if you have 5 over minus st, but the problem here is that you can't simply, like, this is not a stable voltage, right? Like this is like, we can't comment on this because we have a pole at s equals to 0. So yeah, it will be difficult, right? So I will take one example, and you also take one example where it is a stable voltage. Basically you take like 1 by s into s plus 1 into s plus 2, like that, whatever you want to take. So yeah, let's take an example. So basically, what can you say without even doing anything? Like, can you comment on anything? So you might say that what is the gain, right? What is the gain of my OLTFs? They are same, because like if I replace this s equals to j omega, so the magnitude of this is only magnitude of this one. So this is magnitude of this exponential term becomes 1. So the gain is same. So you might say that my gain margin will remain same as magnitude of g of s h of s equals to, not this one, magnitude of g omega equals to e raised to power minus g omega, g of g omega, h of g omega. Is this correct? This is not correct, right? This is not correct. Why? Because even though like the magnitude remains same, one thing will change. The phase will change. Phase will change, right? Phase will change. Like the phase formula will change, obviously. Phase angle will change. Now the phase changes, right? Phase, like due to this one, obviously you will provide some minus omega t phase, right? So if the phase changes, what does that mean? That means that my omega pc will change. Phase crossover frequency will change. My omega p will change. Okay. So if my omega p changes, obviously my gain margin will also change. From graphically also you can understand, right? From here you can understand that if let's say this omega p, right, it changes, it goes around this side or this side, obviously my gain margin will be lower or higher. Okay, depends on which side this goes. So if from everywhere you can understand, obviously then my gain margin changes. Okay, because the gain margin is related with omega p and not omega gc. Okay, not gain crossover frequency, related with omega pc, phase crossover frequency. So my omega p will change, right? So my omega p changes, right? If my omega p changes, then obviously my gain margin will change. Okay, gain margin will change. Now what will happen to the gain margin? Will it increase or decrease? That we have to comment, right? That we have to comment. So for that, obviously we can do it without taking example also, but let's take an example for better like explanation, right? So let my OLTF g of s into h of s equals to some function like this one, 1 over s into s plus 1 into s plus 2. Okay, so my OLTF is like this one, right? So my OLTF is like this one. Now what is my angle? Basically, what is my angle? Angle g of s into h of s equals to simply 90 degrees minus tan inverse 90 degrees is this one, right? So I will again write to do that hard work also, that replace s equals to j omega. I was skipping this one. Okay, in exam obviously you can skip, right? But just be careful that you are not doing anything, you are not doing any mistake, right? Silly errors you are not making. So this becomes j omega plus 1 j omega plus 2 okay, minus tan plus omega 2. Okay, so now, okay, this is not s, this is j omega, right? This is j omega. Okay, so this is j omega. So now, right now, like this is my angle formula this time. So we have already found this one out, right? We have already found this one out. What is my omega pc? So like omega pc for this one needs to go to 180 degrees, right? So minus 180 degrees. So my formula will be tan inverse omega plus, just writing it directly, you can solve it. We have already solved this, I think, previously also. We already solved this, I think. Equals to, this is omega p, this is also omega p, right? And this is 90 degrees. Now we know the short trick, right? What is the short trick? If this is equals to 90 degrees, then obviously if this is x, this has to be 1 over x. So omega p, short trick basically, omega p is equals to 1 over omega p by 2. 1 over omega p by 2. Okay, so basically, right, omega p equals to under root 2. Obviously I will ignore the negative solution. Okay, so my phase crossover frequency is under root 2. Okay, now what is my gain margin this time? Gain margin is simply the inverse of the magnitude of j omega p into h of j omega p. Okay, so what is it? It is simply like okay, I will write this directly, omega p into under root omega p square plus 1 into omega p square plus 4. Okay, so yeah, this is about this one, right? Now let's just put omega p equals to under root 2, right? So under root 2 into under root like 3 times 7 itself, so under root 21. So no, not 20, this is 6, right? 6. So it is simply 3 under root 2 into under root 2, which is 6 itself. So my gain margin is 6 itself, right? So it is in, obviously it is in absolute value in dBs. It will be 20 log 6, right? 20 log 6. Okay, 20 log 6 simply. So you can find that out and you will get your gain margin. Now let's go for the case 2. So this one was case 1. Case 1. Now what if the time delay comes, right? Case 2. This is without time delay. Case 2 is with time delay. Case 2 is with time delay. Okay, so case 2 is with time delay. So now, right now, what will my OLTF like become? So I will just copy this one. Just copy this one. Oh no, just have to paste, right? and I will write this as g dash into h dash of s, right? So which is equals to simply g of j omega into h of j omega into e raised to power minus j omega, right? Okay, so now this obviously here exponential term will come, right here. Okay, so exponential term is coming, right? Exponential term is coming. So again, right, what will be the phase like value this time of g dash of j omega into h dash of j omega? Only one extra term will come up, right? Minus omega will come up. Okay, so time delay. Okay, time delay, I will consider time delay as t. Time delay td, let's consider it as td. Okay, time delay as td. I forgot to consider time delay itself, right? So here like unknowingly I consider time delay as 1. Okay, I forgot to consider time delay. So time delay is td. So this is uh, omega td. So this is in radians, right? Just remember, always remember whenever you using the exponential, right? This is in radians. Okay, this is in radians. So this is in radians. If this is in radians, what is the angle basically? What is the angle? So like again, right? Again I have a like a type 1 system. So again, right, this will contribute minus 90. Again this is minus tan inverse omega minus tan inverse omega by 2, right? So all this is done. So now what I need to find is phase crossover frequency. So for phase crossover frequency, I will just copy this equation. All right. This will be minus 180 degrees, right? And omega will be changed to omega p itself. Okay, so omega will be changed to omega p itself. Now, right now, can we solve this equation simply? The answer is no. Okay, like obviously we don't know td, so let's assume td equals to 1. That is for sure. Let's assume td equals to 1. Else you anyways not be able to solve this equation. So okay, let's assume td equals to 1, right? And also let me color this one and like mention this. What now td is equals to 1, so I will just delete this, right? So now can you solve this equation? The answer will be yes or no. Like in handwritten format you won't be able to solve this equation, right? In a handwritten format you won't be able to solve this equation. Obviously you have to use some calculator, right? Online calculator or any computer, right? So like already I found this one out. Obviously like omega pc is in radians itself, so just convert this everything into radians. Still you won't be able to find this one out because you have tan inverse term here and you have omega p here. Difficult, right? So what you will do is, like obviously this will not come in exam. This is just to show you, prove it to you why after adding a time delay it happens like that, the reasoning behind that. I'm just taking an example. So here like if you put it in an online calculator, right, my omega phase crossover frequency will come out to be 0.664 radians per second. Okay, now here, right, it was under root 2 from what I remember. Okay, under root 2 means 1.414 radians per second. Okay, now I should change this to omega p dash, else we will get confused, right? So what I will do, I'll do this as omega p dash. Okay, so what do I observe here? Observe that due to this omega, like due to this time delay, right, my phase crossover frequency reduces. Phase crossover frequency reduces, right? Phase crossover frequency reduces. So this is important. So my phase crossover frequency reduces. But why is this like this? So due to this like omega p, right, time delay, what happens, I'm contributing some extra phase lag. So due to this time delay, I'm contributing extra phase lag, so it is helping it to like reach that 90 degrees, right, much more earlier, right, much more earlier. So okay, am I speaking it correctly? Omega p, okay, yeah. If this wasn't there, right, if this wasn't there, then obviously this was only minus 90. Now this is contributing some extra angle, so what will happen? Yeah, yeah, I'm reaching my that phase crossover frequency earlier, right? I'm reaching my phase crossover frequency earlier. Why? Because this is also contributing some angle. So my omega p is going up from 0, okay, going up from 0, increasing from 0, right? So what is happening? Slowly it is reaching under root 2, right? But like in the first case, if it reaches under root 2, yeah, it is phase crossover frequency. But in this case, it goes from 0 to under root 2, right? Let's say it goes from 0 to under root 2. So in between, what is happening, this is also contributing some extra phase lag. This is also contributing some extra phase lag. So I'm reaching my uh, phase crossover frequency, like the point where it cuts the negative real axis, right, much earlier than this under root 2. Okay, so obviously time, like why time delay is contributing extra phase lag. If you don't understand phase lag, just watch my network theory video, right? There I have explained like phasor diagram, phasor video, right? So there I have explained what is lag, what is lead, right? Time delay is causing extra phase lag. Okay, so time delay is causing extra phase lag basically. So yeah, this is what we understand, right? So what will be my gain margin be this time? Gain margin, will it increase or decrease if my phase crossover frequency is reduced, right? From this plot you can understand graphically. So generally what happens is magnitude is always monotonically decreasing. Magnitude is always monotonically decreasing, right, for a proper transfer function, as I explained earlier also. So where did I go here? If I say from here, right, so if my omega p has reduced, right, omega p is reduced, so obviously I will lie somewhere around here, right, will lie somewhere around here, omega p will lie somewhere around here. So what will happen to my gain margin? So my gain margin will also reduce, right? Gain margin will also reduce. So obviously gain margin will change, okay, and gain margin will also reduce. Why? Because uh like this omega p has reduced, right, omega p has reduced, so the margin will also be reduced. Like I will just from graphically I got the point that my omega p is moving from this point to this point. Omega p has reduced, so this is from 0 and this is to infinity, so omega p has moved to the right hand side, let's say here. So my margin, right, margin is reduced, okay, the margin to reach to 0 dB axis has been reduced. Okay, so yeah, now like let me prove it to you, like in like written format, right, theoretically obviously. So what is happening to the gain margin? Gm dash, let's say gm dash, right? So gm dash is simply g omega into h dash of j omega, right? Now this is equals to simply like exponential magnitude is 1 itself, so this is g of j omega into h of j omega. So again you put this 0.664, right, 0.664, you put the value of this one. So what do we get? So where was the magnitude? Yeah, whole square. Okay, so this is what you get. So let me just find, like, use the calculator and calculate this value. Obviously we can see gain margin will reduce, so it is 0.664 whole square plus 1 times 0.64 whole square plus 4, right, under root into 0.664, right. So this is 1.68. okay, this is 1.68. so this is GM dash, right. So this is GM dash. Okay, so yeah, this is GM dash basically. So what can you observe? Obviously GM has reduced, right. GM dash has reduced, so my margin reduces, so it tends to become more unstable, right. My margin reduces, my stability reduces. Okay, like this. That's why relative stability parameters came, right. Both are stable, but which one is more stable? So here from this directly I can compare, right. My margin reduces. Okay, so what about my gain crossover frequency? Basically, what about my gain crossover frequency this time? So obviously my gain crossover frequency won't change. Okay, the one thing that won't change, right, gain crossover frequency. So you might say, sir, phase crossover frequency, the phase margin will also not change. Gain crossover frequency hasn't changed, so phase margin will also not change. But what are you forgetting? You're forgetting that my phase formula, right, phase angle formula is changed, so obviously phase margin will change, right. So gain crossover frequency will not change. Why? Like, due to this one. Okay, as magnitude is equal, magnitude will be equal, obviously. So omega gc will be same, right. Omega gc will be same. I won't calculate, right. Okay, because it will take time, right, to calculate. So that is homework for you. It is a third order equation, so it will be difficult for me to calculate. So it will be same, right. What one phase margin? Phase margin will change. Why? Because one has the phase angle formula of this one, right. Okay, let me copy this one. Just wait 1 second. I'll just take another slide, right. This is the second case. So this is let's say, like, this is my angle, right, for the second case. And what is my phase margin? Phase margin is omega g 180 plus this angle, right. omega g omega g omega g is same, right. Okay, and 180 plus this angle is my phase margin basically. Okay, so this is my phase margin basically. So yeah, this is my PM dash. I can name this as PM dash, right. I can name this as PM dash. So now what about my, like, the case one case? So case one is same only. I'll just copy this one, right, because just that extra term omega g minus td came, right. Extra term omega g minus td came. Okay, so this is 180 itself. So this is my phase margin. Okay, so what can I say from here? So this becomes, like, this becomes 90, or like from here you can say that only this extra phase lag came, right. So what happens? My phase margin I can reduces due to this. I can directly say, right. My phase margin reduces due to this. So yeah, I can directly say phase margin reducing. Obviously, if my phase margin reducing, obviously what can I say? Margin is reducing, right? So my stability reduces again, right? From both of these cases, I can say my stability again reduces. So yeah, I won't go too much into deep into this. Just we'll go to the conclusion, right? So omega p, like this is, let's say, uh, normal g of j omega h of j omega, and we have some delay, right? E raised to minus td into g of j omega into h of, okay, let me just write this in smaller pens, right? It's a little difficult. So what happens? This obviously decreases, right? Here I can say my omega p, what happens? Omega p reduces, okay, or you can say decreases. I can say decreases. What happens to my omega g? So my omega g also remains same, okay, not reduces, it remains same. But what about my gain margin? Gain margin also reduces, right? Decreases, okay, margin reduces, phase margin also decreases, okay. What about stability? Stability also reduces, right? Stability also reduces. As my margins are reducing at certain stage, it will cross the, like, gain margin equals 0 and phase margin equals 0, then my system will become unstable. So from here you can see here omega p has reduced, right? Omega p has reduced from 1.414, right? So it was under root 2 here, under root 2 here, right? 1.414, and it reduced, right? So yeah, this is the case. Now I've written the key point also, that that my all the parameters will change except obviously the omega g, right? Gain, crossover frequency, all the parameter will change, right? So yeah, you should know all this, that due to time delay what happens, right? Due to time delay what happens. Now let's let's solve this question. We have a time delay here also. For the block diagram shown below, find the relative stability parameters. So you have to find the relative stability parameters with this, right? With this. So what you should do? So do you just simply put, like, what do you do, like, approximate the exponential? Should you do that? Should you do that? So let's do that and check if option is matching here, right? Let's do that and let's check if option is matching. So what I will do, method 1, right? Method 1, what I will do simply, like, what is the OLTF? OLTF is g of s, h of s equals to e raised to power k e raised to power minus 2s by s. So this is my OLTF, right? This is my OLTF, and if I replace s equal to j omega, j omega, right? Okay, so this is this one, right? uh, so yeah, this is method 1. So method 1 is something like this. So I will just approximate my exponential function, right? So even though this is wrong, not accurate, but still we can do it, okay, if options are present like this, right? This you can do like in ISRO, ISRO exams, or like other exams, right? Other small competitive exams, you can do this, right? So not accurate method, okay. This is not recommended by me, right? Okay, not accurate, right? Not accurate, okay, not accurate. So what I will do, I'll just simply put here like we have to find the range of k, right? Find the range of k. So I will just simply put 1 minus 2 j omega here, and this is still j omega, right? This is still j omega. So what we can do, we can simply apply the Raoult-Hurwitz criteria. We don't need to go to the polar part. Okay, we don't need to go to the polar part. We can simply find the Raoult-Hurwitz criteria for this to find the stability, right? Without going into the relative stability parameters. Okay, so like with the relative stability parameters, you can also comment on the range of k that I will show you just now. Okay. Oh, I should write this question is that find the range of k with help of, so a bit of a wrong part in my end. I should have written it with the help of relative stability parameters. Okay, so yeah, without the help of relative stability parameters still you can do this, right? I told you, right, we can use this approximation in Raoult-Hurwitz. I can use this approximation in Raoult-Hurwitz, right? So we will use this approximation. So even though it is not accurate, still I will use it, right? So this is my OLTA basically. Sorry, okay, one thing I have to note is that this, right, if you are using Raoult-Hurwitz, right, we don't need to write j omega. You can simply write in terms of this s only, right? S only. So I will use Raoult-Hurwitz, right? Hurwitz 1 plus g of s into h of s equals to 0, right? 1 plus g of s h of s equals to 0. So like, okay, what does this become? This becomes this, I can approximate 1 minus 2s divided by s. So 1 minus 2s divided by s into k. Okay, equals to 0. So like just use the Raoult-Hurwitz criterion, right? So just use the characteristic equation. So this becomes s plus k minus 2ks equals to 0. Okay, so this becomes s 1 minus equals to 0, right? So what are the ranges of k, right? So obviously we just need to use the Hurwitz criterion, like obviously that first criterion, right? If you remember, right, keep on revising. What was the first criterion? Up until second order equation. So sorry, up until, yeah, second order equation, all the coefficients of my s, right, should be positive. So this k has to be greater than 0, and this 1 minus 2k has to be greater than 0. So from here I can say that k will be less than 1 by 2. So range of k, right, is 1 by 2 and 0. Okay, so range of k is 1 by 2 and 0. So is this present in the options? So no, I don't see this in the option, right? Okay, that's why I told you, right, this is not the accurate one. Okay, not the accurate one, not accurate. Not accurate enough, right? So now let's solve this using the relative stability method, right? So method 2. But also this also we are not able to solve this time, right? I have a type 1 system, then I am able to solve. If I have pole equals to s equals to 1 or something, then it will be difficult. Okay, let's see why. So this is more accurate using the relative stability parameters. So like we can solve this using two things, using the phase margin and gain margin. So let's solve this using phase margin. Phase margin, what is the condition for stability? Okay, phase margin should be greater than 0. Okay, and gain margin should be greater than 0. So let's first solve it using phase margin, then we will solve it using gain margin, right? So like what is the phase? What is the phase? Phase, like phase is simply minus 90 minus 2 omega, right? Minus 2 omega. So let me replace this in like radian format, right? Pi by 2 and 2 omega, right? I'm writing this directly now. So this is this one. Also, what is like for using the phase margin, I need to find the omega pc, right? Sorry, the omega, yeah, the omega gc, basically the omega gc. Okay, sorry, I'm doing something wrong, sorry. Yeah, sorry, uh, I'm talking about the phase margin, so sorry, I have to find the gain actually. Sorry, this will be for the next case. I was just getting confused. So what is the gain? I have to find the omega gc, right? Omega gc will be what? When the magnitude of this frequency response of the OLTF will be equals to 1 itself. So my frequency response of my OLTF will be equals to 1 itself, right? So my frequency response of my OLTF is equals to 1. Then what does this mean? This is at omega g, right? Omega equals to omega g. Okay, so like let me replace this. So this time, right, it is k by omega g itself, right? Because the magnitude of e raised to power minus 2 j omega is 1. So this is equals to 1. So k, right, equals to omega g itself. K is equals to omega g itself. So this is one condition. So now let's go for the like the make the phase margin greater than 0. So I found out my gain crossover frequency, right? So what is my angle? Angle is this one, right? So I'll just copy, cut, paste this one. Okay, bring it over here. Right, angle is this one. Okay, so for my phase margin needs to be greater than 0, that is for sure. Okay, so obviously I will replace omega g over here. Okay, so at phase margin is equals to what? Phase margin equals to pi plus this angle of g of j omega g into h of j omega g, right? So this is equals to pi by 2 minus like this. I am replacing this angle here, right? This one with this one. So my pi minus pi by 2 is pi by 2 itself, and minus 2 omega g. Now what it should be equals to, like this is my phase margin, right? So this should be greater than 0. This should be greater than 0. Okay, my phase value should be greater than 0 for my system to be stable. Okay, so what is my omega g equals to? Omega g is equals to k, right? So omega g will go into this side, right? Omega g will go into the right hand side. So 2k is less than pi by 2. So I can say k is less than pi by 4. And only one option is satisfying this one, right? K is less than pi by 4. Everything else, right? Everything like this one is always greater than this, and this one is greater than this one is greater than this. So only option A is satisfying. So option A is correct. Okay, like greater than 0, like you can understand from this one also. Okay, so this one also, but k has to be greater than 0, right? It can't be negative. K can't be negative. Okay, that is fine. Now like you might say, sir, but what about the other condition? What about the GM condition? So let's do the GM condition as well, right? So this was for the phase condition, and let's try to solve it using the GM condition. So again, right, keys to for stability, my GM should also be greater than 0. My GM should also be greater than 0. Okay, my GM should also be greater than 0. So if my GM is greater than 0, what does this mean? This means like this is 0 dBs. So in absolute values, right, absolute amounts, this is 1, right? Okay, without unitless amount. So GM should be greater than 1. So basically, right, so for this I have to find the first the phase crossover frequency, right? So again I will copy the angle formula, right? Okay, if I just paste this one here, it will come. Yes, luckily it came, right? So I have to find the phase crossover frequency. Okay, so at phase crossover frequency, what is the angle? Equals to minus pi, right? Minus pi. Okay, so this becomes minus pi by 2. Okay, equating these two equations, right, equals to minus 2 omega p. Okay, just equating this equation equals to minus pi, right? Just doing that. So my omega p equals to pi by 4 itself. So my omega phase crossover frequency is pi by 4, right? Now let's find the gain margin from this one. What is the gain margin? Gain margin is basically the reciprocal of g of j omega p into h of j omega p. Okay, so what is this? So obviously, right, what is my gain formula? Gain formula is this, right? K by omega g. K by omega g. If you see it correctly here, so it is simply k by omega g, right? So no, k by omega basically, k by omega p. So gain, like, it will be k by omega p, and this has to be greater than 1, right? This has to be greater than 1. Okay, so k by omega p has to be less than 1. Okay, for stability. Okay, for stability. Okay, this is also for stability. If I mentioned here. What is omega p? Omega p is equal to pi by 4. So I get the same condition again, right? Same condition again. So omega p is like equals to pi by 4. So obviously, like, you can see from gain margin also, from phase margin also, you can, like, you are getting the same result. So obviously option A will be correct here, right? Option A will be correct. So you just check with options, you will figure out, right? You will figure out. So now let's go to the next question. This is the next one. This is the gate question 2011, right? So this is very simple question. Okay, just read this question and try to solve it by yourself. What is this telling us? The frequency response of a linear system, g of j omega, basically unity feedback system, is provided in the tabular form. Okay, so like the angle and the magnitude is provided for various frequencies, right? So the gain margin and phase margin system. So again, right, what is the definition of gain margin? What is the definition of gain margin? Definition of gain margin is basically the margin that is required when my phase is minus 20 degrees. So, or you can say the inverse of my magnitude. Okay, in absolute scale. Okay, normal scale. In log scale, it is a margin you have to add, right? So here is my phase minus 20 degrees, and this is my gain. So inverse of this one is 2. So let's solve this basically. So gain margin omega p into h of g omega p. Okay, so it is 1 divided by 0.5, so it is equals to 2. It is equals to 2, right? So if it is equals to, now what is, like, you have to find it in dBs because the options are present in dBs itself, right? Not in normal units. So gm in dBs, right? Twenty log 2, and log 2, you should remember that it is 0.3, right? Log 2 is 0.3, like log base 10 2 is 0.3. You have to remember this because this one will come hundreds of time, right? So this is, if it this is 0.3, so this will come out to be 6 dBs. Okay, 6 dBs. So first one is okay, 6 dBs is okay, right? And gain margin is positive. Okay, I can see gain margin is positive. Why? Because, like, from here also I can see that this is the point where my gain is 1. So this is my gain crossover frequency, and this is my phase crossover frequency. So my gain crossover frequency occurs earlier than phase crossover frequency. So my gain margin will obviously be positive. So yeah, my gain margin will obviously be positive, and my phase margin will also be positive. So, like, what is phase margin? The amount of margin, that the amount of phase lag that I need to add when my gain is 1, right? So how much phase lag I need to add? Phase lag means amount of negative angle I need to add, right? Negative angle I need to add. So this is minus 150 at when my gain is 1. So this minus this is minus 150 when my gain is 1. So I have to add minus 30 degrees with it, right? Minus 30. So what is the amount of phase lag I need to add? I need to add 30 degrees. So 30 degrees is the positive, like, is the angle and track, but it is a negative angle. So minus 30 degrees. So phase margin is 30 degrees itself. So don't get confused by that. Don't get confused by that, or simply use the formula. Simply use the formula and you will never get confused. What is the formula for phase margin? Okay. Phase margin is 180 degrees plus g of j omega g into h of j omega g, right? So you will never get confused. Just use the formula and be must, right? Be must. So else you just understand by that the phase like concept. So phase margin is how much? This is 180 itself. And what is the angle? Angle is basically minus 150 here. So it will be minus 150. So this is 30 degrees, right? So this is 30 degrees. Obviously my option A is match. Obviously I can say that phase margin and gain margin positive anyways, but still just to prove it to you that yes. So this was very simple, but this may come, right? You might get confused, so that's why I have to take this question. Another question that I have to take, right? This is also another type of question. Very simple question, just 1 second question only. But again, you might get confused with the terminology, right? So the critical value of gain of a system for a system is 50. Now, what does this critical value mean? Just resume, right? What does this critical value of gain means? Just think about it for a second. Again, the system is operating at a gain of 25, but it is saying critical value is 50, but the system is operating at gain 25. Find the gain margin of the system. Okay, how to find the gain margin of the system? So let me plot a polar plot and explain through there, right? We plot the polar plot. So let's say current gain of system is 25, so it is operating at 25 gain. So this is, let's say, like k desired. So a desired gain for my system, I want to operate at k desired. So this, let's say this is the gain. Okay, I will explain everything. Just let me draw 2 curves, and there also we will understand better, right? Oh shit, no. So this is k critical. Now what does this k critical and k desired mean? So what happens if I just multiply this whole thing, right? This is the point, this is a gain at which this is operating. Okay, so let's say my gain of g omega and h of j omega is 1 itself. Okay, I'm just multiply k with this one, right? So multiply k with this, and this will become k, right? So the k is the varying parameter which is varying the gain. Okay, varying the gain. So if I just multiply k with this, obviously it will get expanded. If I multiply like k critical is greater than k desired, then it will get expanded. If I multiply some k which is smaller than this k desired, it will get contracted, right? It will be less. Okay, so I have your understanding. If I multiply something more than 1, it will be more. So what this k critical means? K critical means just the amount of k, the gain that I need to multiply so that it may cross the critical point. That's why this is known as k critical. Critical point is what? Minus 1,0, right? Minus 1,0 is the critical point. So it should just cross that. Until before that, it is fine. It is not crossing that point, so the system is stable. Okay, that's why this is known as k desired. So I want my system to be stable, hence I make it k desired, right? So now, like what I can write? Let me write my g of s, h of s. Okay, like this one, k by s tau 1 plus 1 s tau 2 plus 1, right? So here, right, you can see that my gain of my old TF is k itself. All this is fine. Okay, like I mean, like that gain is k. Like the main gain is depending on k itself, right? Main gain is depending on k itself. Okay, so if I multiply k, this will be expanded or contracted. Gain varies with k. Okay, obviously if I vary omega, that will vary, but if I keep my omega constant and vary k, gain will vary with k. Okay, and like this is order 3 system. Okay, and ending at this minus 270 degrees, and obviously starting from minus 90, right? So this is this one, right? This is this one. Now what about my question, right? So what is the question asking? Question asking find the gain margin. So from here, can you tell me what is the k desired? K desired is, or you can say k operating, right? Or k operating. In what gain it is operating? It is operating at 25 gain. Okay, so this is operating at 25 gain. And what is the critical value of gain? 50. So if my k critical is 50 and k desired is 25, then how can I find the gain margin? So at this point, like my k, like just write this simple formula. Whatever the omega g, like what does this gain like this phase crossover frequency depend on? Does this phase crossover frequency depend on k? So omega p is not a function of k, right? It is not a function of gain itself. It is only function of uh, like the phase itself, right? Like only the phase, right? So it is not a function of k, not a function of k. So it's not a function of k. So omega p will remain same for both cases, right? Omega p will remain same for both cases. So omega p is like same for both cases. So if my omega p is same for both cases, what can I say? Only the gain margin will change, right? Gain margin will change. So first, this is the, let's say g gain margin will change. Okay, so what I can say, like for this case, right, what is the gain margin? Like if my k is k critical, what is the gain margin? Gain margin is 1 in absolute values, or in dBs it is 0, right? It is 0. Okay, I will say gm operating, right? Gm operating, what is the current gm when the system is operating? Gm operating is so still I have this much distance, right? K desired. So obviously, like the my gm operating will be inverse of this one, right? Inverse of this magnitude of g omega p into h of g omega p, right? By 1. And what is this equals to? So simply this will come above, right? I will copy this one. Okay, I haven't put in this one. So this will come at the top. This will be omega p tau. Okay, this will be magnitude. So omega p tau square plus 1, right? And this is divided by k desired, basically k desired, right? So this time my k value is k desired, right? So this is asking my gain margin of system. Okay, this is basically asking the gain margin at which my system is at with the gain at which it is operating. So I have to find this gm operating. How to find this one? We'll find this one, right? Now what about my gm critical? Gm critical value I know, right? It is equals to 1 itself. Why? Because like here obviously it is crossing the -1 point, a critical point at when it is crossing the negative real axis. That is why this is known as k critical. Definition of k critical itself means that gm should be 1. Okay, it is crossing my negative real axis at the critical point. That is the definition of my k critical. Just keep this in your head, right? So this one, this is equals to 1, but my phase crossover frequency isn't changing, right? It's still same. So the this numerator will be same, but the denominator will change. This will be k critical this time. Okay, I'll just mark this one as red and this one as green. Okay, I'll just take another page. So now, right, I'll just take the ratio of these two, gm operating and like gm critical. So gm operating and gm critical is 1 itself. So we'll get only gm operating itself, which I will write simple gm because that is the gm of the system, right? Not like this. Have I put the mod sign? Okay, I shouldn't have put the mod sign. Sorry for that. So yeah, gm should be equal to the ratio of these two. So what is the ratio? So this is like this one will get cancelled, right? So k critical will go above and k desired will be at the bottom. Okay, k critical and k desired. Okay, so this has different names also. So this is the formula, right? Just remember this, right? if you can remember, or I have derived to you that how to derive it, right? So this k critical is also known as my k critical, like these are just names, right? Nothing else. K marginal, okay, because like it's just marginally stable, that's why. Okay, and this k desired is known as k operating, right, as I mentioned earlier. So just be careful of that. This is just a terminology, okay, don't get confused by this. Okay, so from here I can simply use the formula. What is k critical? K critical is simply uh, what is k critical? K critical is 50, right? And what is k operating? 25. So 50 upon 25 is 2, right? Hence, like I can say, like only from I have only gain margin, right? I don't have phase margin. So from this I can comment, like if I want to comment, it can be stable, right? But as I don't have phase margin, I should not comment. And what are my gain margin in dBs? Gain margin in dBs, obviously. I told you to remember, right? This will be 6 dBs, right? 20 log 2 best into is 6 dBs. Okay. So yeah, that's it. For the polar plot. Okay. So we are done with this chapter, and next we'll start with the Nyquist plot, right? So in Nyquist plot, first we'll learn about the mapping theorem on all those things. So many teachers don't teach you this, like how does this Nyquist theorem came, and what is the derivation of that. Okay, how did this came? So in polar plot also I derived almost everything and told you the intuition how to approach each problem, right? So I hope you like the approach, and I will see you in the next lecture, that is the Nyquist plot basically.